I'll open with a prayer. Dear Heavenly Father, we thank you for this time to gather as a group and hear about the wonders of your universe. Thank you for the beautiful day that we have, and ask that you be with all of us as we go about our time until we meet again. Also be with those in our congregation and families that are in need of your healing touch and prayers. Bless this day. Amen. Now, I have a couple of announcements for you all. First, we announced last week Phil Metcalf passed away. Long time participant in the Tuesday morning fellowship. His memorial service is next Monday, week from yesterday, week in the future. On Monday, 2 p.m. You can attend in person or on live stream. It will be live streamed also. Go on the Westminster.org site and click on the streaming that you normally would on a Sunday morning for the streaming piece of it. It will also be archived if you want to look at it on a replay basis. So that's next Monday, 2 p.m. is the service. Okay, and we have a few other announcements. Craig, I think you have an announcement.
We have a field trip in 2 weeks to Bailey's Farm, which is out in Pecos and Unionville, and it's a 122-acre dairy, and it's a Pennsylvania dairy of distinction. If you want to come, there's flyers in the back of the room which will tell you more about it. Please sign up or let Dave Goodale or Ted or me know so we have a count, but you're welcome to come and bring your spouse or friend or whoever you want to. That's in 2 weeks.
Can we bring our girlfriend?
Sure, if you like.
Okay.
At your own risk.
Yeah, if you're brave enough.
Bring your wife too.
Thank you, Craig. Okay, Dave Walter, would you come up and do the honors of introducing our speaker of the day?
Okay, our speaker today is John Conrad. He's coming to us from Portland, Oregon, so I assume the signal's bouncing off billions and billions of stars to get to us here. John spoke to us last year. He's a retired scientist. He's a public ambassador for NASA. So without further ado, Mr. Conrad.
Let me make sure everything's on here. Can you all hear me?
Yes.
And here I sit in Portland in a hotel room. 3 hours earlier, but we're up bright and early every day. I really appreciate the opportunity, and let me see if I can get my slides up here and we'll get started. And I would note that it's a particularly helpful thing that we've been able to reschedule this to today, because we actually are giving you a talk about something in advance of the something which you've been seeing probably in the news about a NASA spacecraft. And had we done it a week later as scheduled, I actually would have been on a plane at this time, so I couldn't. So I appreciate your adjusting your schedule, and it's very helpful to the timeliness of the talk. All right, here. So you should be looking at something that says turn on sound.
Yes, we see it.
Good. And I've learned enough about Zoom to learn when I can transfer through the noise in my slides and turn it off. So here we go with the presentation. The term NEO is well known in the space community, and you may have heard of it. And if you ever watch Neil deGrasse Tyson specials or anything, you probably would have heard of it. At any rate, these near-Earth objects are simply that. They're in orbits around the sun, like every other object in the solar system is orbiting around the sun, with the exception of a very few objects that are moons of something like our moon. But everything else, the uncountable number of things, all orbit the sun. And some of them have orbits that pass across Earth's orbit. In other words, they're what's called aphelion. The furthest part of their orbit is beyond Earth's orbits, slightly or exactly Earth's orbit, and therefore we have to watch out for when these near-Earth objects might actually arrive in our orbit around the sun at the same time that we do, in which case we get something like this. And as you referred to the wonders of the universe and thanking our creator for that, among other things that was created is gravity, which keeps all these objects not just orbiting, everything orbits, but perturbs the orbits from time to time. And so we have to watch out for particularly large versions of these near-Earth objects that might be on a path to impact the Earth. And so I thought the best way to start would be with a look at one of these dangerous things that happened not very long ago. And so hopefully you saw what was on the dash cam as this vehicle drove down the road 9 years ago, the day after Valentine's Day, and the burst of what's called a bolide, which is a kind of a meteor that comes in and then bursts in a fireball before it hits the ground. And it was a very large burst, and you didn't hear anything. And part of the reason is because of how far away it is, but also it's because it was in Russia. So here it is again. And you can imagine that in this city, in central Russia of Chelyabinsk, the literally hundreds, if not thousands of people that happen to see this happen, as you see, 14 miles in the air and about 20 miles away, so maybe 30 miles direct line away from them, were pretty startled to see it. Yeah. And what took place next, as happens because the speed of sound, as you're aware from thunder and lightning, is a lot slower than the light that you just saw. And so a mile every 5 seconds means that it was something on the order of 2.5 to 3 minutes before the sound from that tremendous burst reached this city of Chelyabinsk. And by that time, many people had called their friends or their family and said, take a look out there, and told them the direction. And everybody's standing at the windows when this occurred. And so what you're seeing there, hopefully you could hear that. If you couldn't, that's something I ought to fix so you can hear it. But hopefully you heard that and saw it, and I'm going to play it again so you get another chance. But what that was simply an automatic camera hanging under the eaves of an apartment building. And when the shock wave hit, it blew the camera off its moorings and it flopped around and recorded the sound. And much of the sound you could hear was breaking glass. So let me ask, did you actually hear it?
Yes.
Good, good. So fortunately, and only good fortune, that this didn't actually burst over a populated area, because it was a 0.5 megaton equivalent nuclear device called an airburst in weapons terms. And there were no fatalities, but as you can see from the glass in the lobby of this entertainment center and the damage to brick buildings in particular, there were well over 1,500 people that were injured by the glass because they wanted to get a look at it and they looked out the window and got injured. So it was pretty devastating, but fortunately no fatalities, only because it wasn't near a population center. So that's the nature of kind of a medium-sized threat from these near-Earth objects that happen to actually collide with Earth. So what is it that makes up the NEOs? Where do they come from? On the top layer of this slide, you see the word Halley. So you're familiar with Halley's Comet, which comes back every 76 years or so. All these comets they go out beyond the furthest planet, Neptune, and then come back around on a very predictable basis. And as they get near the sun, as they pass through the asteroid belt and past Mars on the way in towards the sun, it gets warm enough, even though it's very cold, that all of the trapped snow and ice in these dirt balls, if you will, is vaporized and explodes and causes the tail that we see that has us call them comets from, ancient times. So they come from beyond the planets. We used to call them dirty snowballs, but it turns out they're not that different from asteroids. They're mostly made up of dirt, which is to say grains and rocks of various sizes, trapping a lot of snow and ice, and that's what causes the tail. So a lot of comets, very predictable orbits, give us these meteor showers at times with what they scatter into space that the Earth passes through. But by far the most number of NEOs that are in orbits that come near to Earth are the asteroids. And you see kind of a cute, whether it's a seal pup or a sea otter looking asteroid there at the bottom that a Japanese spacecraft visited. But at any rate, they come in all shapes and sizes. And when they're well behaved, they're in what's called the main asteroid belt, which we all learned about in school when we learned about the 9 planets, now 8 planets with Pluto demoted. But at any rate, between Mars and Jupiter is a very vast distance. And in that area of space are uncountable numbers of asteroids that are well behaved in terms of just orbiting the sun as we do through the eons. But from time to time, and when you have 4.5 billion years to work with, as the solar system does, even with one collision a year, you've got an awful lot of asteroids that have run into each other. And part of what happens is they lose energy and they go into an orbit that's closer in than being between Mars and Jupiter. And so those account for the largest number of the near Earth objects. And the question then, of course, is do they ever hit the Earth, not just come near it? And of course, you're aware that they do. We've all probably seen shooting stars, which are meteors that we see streak across the sky and disappear. And meteor is the name that we give to any of these things, be it comet matter or asteroids, as they enter our atmosphere. Sometimes, like the one you just saw at Chelyabinsk, they explode before they hit the ground in what's called a fireball or a bolide, technically. And then finally, some of them do get down to the ground, and those are what we call the meteorites. So enough terminology. And you probably read in the news or hear sometimes from the quasi-scientific sites who love headlines, you'll hear about an upcoming meteor storm or something like that, which frustrates people that take these things seriously because there never is something that looks like this to a layman. Some of the best showers, and they're very predictable because they're leftover comet tails that orbit the sun very predictably, like the Leonids in November and the Pleiades, the Perseids that just took place in August and do every year. They get advertised as, watch for the meteor storm. But if you get a frequency of streaking bits of comets that you can see once a minute, that's an extremely high frequency. So it isn't like seeing a storm of streaks, although they love to illustrate it that way. So many things, and in fact daily, do hit the Earth's atmosphere, and frequently a number of them hit the ground. But the question then becomes, in terms of dangers, has anything big ever hit the Earth? And you're probably well aware that it has. From time to time, we get big collisions with the Earth. The best known, based on a theory that's now been challenged and never proven wrong, and so is probably true from the geologic record from about the 1980s when it was put forward, is about a particularly large asteroid, 10 kilometers in diameter, about 6 miles across. You see the equivalent energy release when it hit the Earth there 65 million years ago of 2 million hydrogen bombs. And you see the size of the crater that it created just north of the Yucatan Peninsula in the Gulf of Mexico. And the crater we have located and measured, and it's as big an area as Lake Erie, but much, much deeper. So it was a tremendous explosion. And in that explosion, and most of the damage comes not from the blast wave and the heat, which certainly killed any living things nearby, but because it lifts so much material, hot material, into the atmosphere, which very quickly covers the Earth and blankets the Earth for years. And in those years where solar energy doesn't get through to the surface, the mass extinctions that you may have heard about, in particular the dinosaur species, died off. Had the human species been there at the time, it would have died off as well. So a 10-kilometer collision with the Earth, and these size fortunately happen very infrequently, as we'll see, would be devastating to our species. The next one, I'll just fast forward most of the way, but to about 50,000 years ago instead of millions of years, is the evidence provided in eastern Arizona by a very large crater of something that we call the Barringer asteroid, the Barringer crater. And it's not nearly the same size as the one I just talked about, but it is a pretty big equivalent nuclear weapon, 5 megatons. It did cause a big diameter approaching a mile, and it's very well known. And the reason that it's well known is because perhaps some of you, I have, visited this crater because it's just a few miles off the exit that's well advertised with signs like this of the interstate in eastern Arizona. So a lot of Americans and others visiting and touring the United States pass by this exit and decide to go visit it. You can see in the lower right of the, or the lower left of the rim there, the road coming into a visitor center, so you can get yourself a snack and hear some information about it and go out to the crater and look over the rim and so on. It's pretty impressive. And the scientific studies have concluded that it was a very steep, mostly metallic asteroid that reached the ground. And you might wonder, why haven't you heard about other craters if you've heard about this one? And the fact is, it's mostly because it's in the US at a place where they could market it and put up a sign for it. And so lots and lots of people know about it. But it's not all that large in terms of what actually has been found as the scientific survey teams have gone around the world looking for craters. So there's a wonderful database that is known as the Earth Impact Database with this web address, easy to visit, easy to navigate through. Every one of these red dots is a crater that's been located and studied, the age of it and the amount of energy of the impact of the meteorite that hit is estimated. And so you can get all the information you want with the locations about all of these red dots that you see. And one thing you might think about is, well, that's those that they've found on the land. And we know that the Earth is 3/4 covered by water. And so we don't get to see the evidence in the water, nor do we in the ice sheets, which melt periodically and don't have any lasting evidence on the surface of impacts. So roughly 4 times as many impacts through the eons could be found if we could look there as well. So 4 times the number means that there's on the order of 1,000 impacts through the 4.5 billion years that we still have been able to find physical evidence or estimate that we could find physical evidence of at this point. So they're not infrequent. They're pretty easy to find. Just for comparison, when you go through the database, you'll find that 3/4 of these 190, more than 140 of them, are actually bigger than the one in Arizona, which would be very devastating as the size of a nuclear weapon if it hit populated areas. So there have been lots of those. And the very biggest ones include the Chicxulub, the 10-kilometer one that we've talked about. The other 2 are Vredefort in South Africa and Sudbury up in Ontario. So they're very large, and as you can see, we've looked hard for anything that big and only found 3 of that size on the landmass of the Earth. I've looked through the database thoroughly to see if there are any in Pennsylvania. Turns out there aren't. The closest ones are down near the bridge tunnel at the south end of the Chesapeake Bay and up in just north of Lake Ontario, 200 to 300 miles away, I think these are. But that's just the ones that have been found and the positioning of us in Pennsylvania. We'll just move the clock forward almost to today and go to the last century, the 20th century. And early in the 20th century in eastern Siberia, a place called Tunguska, there was recorded by seismic measurement devices a tremendous burst in the atmosphere. As it turns out, that area of eastern Siberia had virtually no civilized people anywhere near it at the time. And that's not to say that indigenous people aren't civilized. My point was there was no society there, no population near there. So nobody in the scientific community in the early 20th century was looking at this or recording anything about it immediately. It took about 20 years to get the first scientific team in there to interview the indigenous and to get their stories, and to learn that apparently there were no casualties, or I should say no fatalities, and only a few people had a record of witnessing this. It was the equivalent of a burst even bigger than the Arizona crater had caused. And it was very clear, even 2 decades later, where it happened, because there were millions of trees all lying down with their trunks pointing back toward ground zero. And so this tree blowdown gave them the ability to know exactly where the airburst had taken and blown all the trees down. So as I said, this is the most dangerous recent impact, except for the fact that about 100 years later, as I said, 9 years ago after Valentine's Day came Chelyabinsk, which wasn't quite as large, but it was a very dangerous one, which also fortunately didn't lead to any fatalities. So we've had a couple fairly dangerous things if they'd been near people in the last 100 odd years. Now came, and I say now because the scientists had known about the danger of NEOs for a long time, and now came in '94 an event that I imagine a number of you remember. There was a comet discovered by a comet hunting team, a couple known as the Shoemakers, who were astronomers, and David Levy, who's a well-known amateur astronomer. And separately and together, they have found many comets that have gone into the International Astronomical Union database of comets and had their names put on them, just as this one was. And in about '92, I think it was, they watched as a comet came very near to Jupiter on its way in toward the sun. And because of Jupiter's very great mass and gravitational attraction to the comet, it broke it into pieces. And they were able to calculate that in July of 94, on its way back out on its elliptical orbit, it would pass not just close to Jupiter as it had on the way in, but it would actually impact Jupiter. And so in one of those wonderful serendipitous timing events, the Hubble Space Telescope was finally fully repaired, and all of its instruments, including its ultraviolet camera, were operating, so that we were able to observe in July of 94. I actually was down at the Franklin Institute with people that went down there to look at it. This take place as all of these large fragments that the comet had broken into impacted Jupiter. And ultraviolet was very important because it allows us to use the size and various spectral characteristics to estimate the energy release of the impacts. And what they found was that the largest of the 21 fragments that we were able to see impact Jupiter was about the same size as a dinosaur killer. So all the scientists that had wanted to get some attention given to these dangers could now call up their government leaders, maybe politicians, and point out that we just witnessed a neighboring planet have an event that if it had been us that had been hit by this, it would have caused the extinction of our species, which kind of got the attention of the politicians. And they did the important thing, which was loosen up the purse strings and set up a NEO program office, first out at Jet Propulsion Lab in Caltech in California. And through the years, they've actually set up a more serious office at NASA headquarters in terms of decision-making power. And the Caltech group has reverted to being a very important part of the NEO community, which is called the Center for NEO Studies. And I point you to this simple to write down and remember website, CNEOS at JPL, because you can go there anytime and the information changes almost daily, and see what the results of the funded efforts to survey the sky, build up a database of these near-Earth objects, how big they are, what their orbits are around the sun, what might be their close approach to Earth, hopefully not hitting Earth. And they have a wonderful page on the website called Close Approaches that changes pretty much on a daily basis. It predicts in a nice, easy to read table what will be the next 2 months. And it's usually 50 or so close approaches. And close doesn't mean hitting Earth, but sometimes it means coming within the distance of the moon, and sometimes even maybe within the distance of, say, the communication satellites, 20,000 or so miles away. Those are pretty rare. But obviously you can scan the table, you can look for the close approaches, you can look because they estimate the size for the very big ones, and breathe a sigh of relief, or at least I do, to see that it's going to miss us by 2 million miles, but know that it's up there and it comes back periodically and could someday. So how do we populate this database? How do we calculate the orbits? Let's talk about that for a second. The funding allowed survey telescopes to really pick up the pace of looking for NEOs so that we know what the risk is near Earth and can keep track of it. In the 90s, we had the MIT Linear Survey Telescope operating and doing a pretty good job even before the funding was increased. And after the funding was picked up, the Catalina Sky Survey and the Pan-STARRS, and these are all ground-based telescopes, picked up the task of doing nothing other than surveying the skies constantly and repeating the survey in order to find and calculate the orbits of near-Earth objects and populate that database. And as you'll see in a minute, the pace of finding them is pretty impressive at this point. In addition to the ground-based telescopes, you may or may not be aware, infrared is a more useful tool for looking that you don't have the advantage of using from the ground because of the atmosphere. But NEO-WISE, a NASA spacecraft, is out there, and it is on a regular basis surveying the entire sky. And the I in WISE stands for infrared. And so it can look in a region of the spectrum where it can see things that are cooler that can't be seen from the ground. So it finds a lot of, if you will, complementary families of near-Earth objects. So the pace of counting these and finding them has been steady and accelerated. So I want to share kind of the awesome reality of what's out there with this animation, which I'll start shortly, but I want to explain what you're looking at here. So you've got sort of a God's eye view looking down on the solar system from above with the sun in the center and the Earth, the third one out, and then Mars. And beyond Mars comes Jupiter, which is outside the box. The gap is so great. And as I said before, that's where the main asteroid belt is. And so there are going to be two kinds of objects that will populate this as we move through time from the year 1800. In 1800, we pretty much not had the technology to find those asteroids with ground-based telescopes. But you may or may not know, in about 1802, I think it was, the largest of them, which is known as Ceres, was discovered. And it's on the order of the size of Pluto, and it was a planet. So that kind of drives home the point that these things aren't, nothing in the solar system is necessarily a planet or not until we decide to set up a naming convention and define that as a planet. So we called Ceres a planet. And through the 50 years from about 1802 to the middle of the 1800s, I think there were on the order of 6 or 7 asteroids discovered that were big enough that they were added to the list of planets, along with Mars and Jupiter and everything. And they realized that this wasn't going to work. They had to demote them back to being just, they called them minor planets, because there were going to be far too many of them. So they stayed as asteroids, and we went back to the naming convention that had planets being just the very large things. At any rate, when I start this up, you're going to see what's in the database of the Minor Planets Center there. You see in the bottom website address. They keep track of all of these objects. And first, we will jump a century forward, and you'll see how many they discovered in the 19th century, and then through the first half of the 20th century and so on. So I'll just go through it here, and you can see. So here we have 100 years later. They've found quite a number of asteroids. By the 1950s, they'd found many asteroids and only a few near-Earth objects. By the beginning, by the 90s, they'd found many more. And after the funding began in 99, and by the end of this animation in 2013, which is when we got this animation to show you, this fairly awesome view of what's in the asteroid belt out there beyond Mars. These are all, every dot there is a known numbered item in the International Amateur or Astronomical Unit's Minor Planet Center database, over 600,000 as of 9 years ago, and almost 10,000 of them were near-Earth objects. Those are the red ones you see there. And that's kind of impressive, except that was 9 years ago, and the pace with these survey telescopes continues to accelerate. And so I'm going to show you going from 10,000 in 2013. With my latest check of the database, I found that now the count is up to 29,000. So we're adding NEOs to the database at a rate of 3,000 a year or more now. The success of this NASA, which means taxpayer funded, like by you and me, program has been really incredibly successful in terms of identifying what's out there so we can keep track of it. 99% of them have been found. since the funding began. Looking at the ones that are a size that we consider to be potentially hazardous, which is over 140 meters, which is bigger than the Arizona Behringer asteroid, bigger than either the Chelyabinsk or Tunguska, quite a large asteroid. Those are defined as potentially hazardous, and over 2,000 of the ones we're tracking are of that size. And if you look at the really big ones, not quite as big as the mass extinction ones of 10 kilometers, but look just at 1 kilometer and above, we think that even though you might not have the kind of years-long winter that was caused by a 10-kilometer, you will have enough damage to the infrastructure of Earth that civilization won't be able to actually support itself for some period of time. So we do not want one of these 1 kilometer size to reach us. And there are a number of them out there that we've found, and that's the bad news. But the good news is they're easy to find, and we keep looking. There's another NASA spacecraft being launched in a few years, I think called NEO Surveyor, which will go in towards the sun in order to look out at Earth so that we won't miss any that we might miss because these telescopes can't look toward the sun to find them. So we expect the count to be picking up even more in a few years, and we can find the most dangerous of them. And so you can probably guess by now that there have been no serious impact threats found. And modern computers and orbital mechanics and physics are very reliable. And so we're actually able to not only find these things, but make repeat visits to them with the survey telescopes and continue to update their orbits out for 100 years into the future. That's very easy to do. And the reason we revisit the objects that we have put into the catalog frequently is because there can be perturbations, a passing comet or something else that causes an orbit to change. And so even though we might feel good about knowing that there are no impact threats, someday there will be one that has our name on it. And then the question becomes, what do we do about it? And the answer is something that as a kid I might have thought of as science fiction. And I think it's kind of neat. We have a planetary defense office. We have a planetary defense officer, the highest US official at NASA headquarters for our country to keep us abreast of how we can defend our planet against the near-Earth objects. President Obama set up a formal office in the NASA headquarters about 6 years ago. And as I said, named the Planetary Defense Officer in NASA. And if I haven't mentioned it, the effort isn't just a US effort. All nations, because it's a global problem, just like climate change is, all nations are focused on planetary defense now. A number of the developed nations have also got their planetary defense missions and officers, and these organizations cooperate with each other. They have their own strategies and plans of what to do to deal with the threat. We published the US's preparedness strategy and action plan. And for the rest of the talk, I'm going to talk about a key part of that plan, which is to meet goal 3. Goal 3, in essence, is when we find the bad actor that's big enough and has a high enough probability that it's going to cross our orbit when we're there and impact us, we want to be able to deflect it if possible. And so that's the technique and the approach that we are trying to put into our arsenal, if you will, as a capability to use if we do find one of these. What does asteroid deflection mean? Well, it's got a technical definition. It's not much. we have to change the velocity vector, the direction and speed of the near Earth object that's headed for a collision with us only about an inch per second, which doesn't sound too much, except when you propagate that over not just seconds and hours, but years. And as I said, we can predict these things not just years, but decades out. It does allow you, if you can nudge it that much, to move it off of its current trajectory and make it miss the Earth. But you do need time. You need many orbits in order to do that, because it's very difficult to move one of these massive objects, even as much as a change of an inch per second. So the techniques that we have now researched for over a dozen years, and then slowly but surely with funded research in the labs and computers narrowed down, has got several techniques that are being thought about. The friendliest of them, as indicated by the green box here, is something called a gravity tractor, which you may have heard of. Simply that means sending a large, massive spacecraft out to the dangerous asteroid, parking next to it. And by doing that, because of the wonderful law of gravitational attraction, every two masses that are near each other will pull on each other. And it's not to say that we have a spacecraft that's anything like as massive as the asteroid that will be the danger. But if we can be out there for enough years nearby and slowly direct the spacecraft in a direction that will tug gravitationally on the asteroid, we can move it that bit of deflection that will make it not hit the Earth. So that's one that we hope for. We'd love to use that because it's very benign, but you need lots of not just years, but at least a couple decades to have it work. At the other end of the spectrum, which is the kind that Hollywood loves to hear. So here's a picture from Armageddon, one of the two fairly cheesy movies of the 90s that talked about NEOs and what to do when we discovered them, or I shouldn't say talked about it. They had Bruce Willis and others dramatize going out there with a nuclear weapon and blowing up the threat, which sounds good. And in fact, for a very large object, it might someday be necessary, but it carries its own risk, because we understand the asteroids all to be the result of many small pieces in that orbit, originally between Mars and Jupiter, that pulled together to make ever larger masses, not as large as planets, not as large as a planet that could sweep out the entire orbit, but nonetheless, they are pieces held together by their mutual gravity, which we call rubble piles. And so all asteroids to some degree are loosely bound pieces. And if you blow up a nuclear weapon, either on or near one, you may take a very dangerous threat and turn it into half a dozen medium-sized threats that are still on the wrong path coming towards Earth. So it's not necessarily a great answer, but we'll see in the future. The one that we want to find we can have a useful approach to, we simply call the kinetic impactor technique. So it's hitting an asteroid hard enough with something in order to hit it real hard and change its velocity vector enough to deflect it. So that's what we're going to talk about from now on. That would be the preferred technique if we can demonstrate that it actually works. And so now I'm going to move to the second part of the talk, which talks about the upcoming demonstration of that to demonstrate progress. And to do that, I need to go to my other talk. So if you give me a second here. I'm going to turn off the sound so we don't get it and share these slides. So hopefully you're seeing the DART slide here.
Not yet, John.
Not yet, so it's not there?
No,
Let's see. Huh. What are you seeing?
turn on sound.
What's that?
We're just seeing the turn on sound screen.
Huh.
Maybe you have to unshare and reshare.
Let me try that.
That sometimes will fix that issue.
So what do you see now?
Turn off sound.
Okay, good. We're on the right one. So now,
There we go.
okay.
Dart double asteroid.
So this is probably somewhat anticlimactic because I imagine a lot of you have seen the news about this. NASA's gotten pretty good at public relations, and there are a lot of reputable as well as frankly unreputable quasi-science media that are putting out the news about the double asteroid redirection test, which is coming very soon. As a matter of fact, next Monday will be the impact, as this artist's concept shows here, of the NASA spacecraft slamming into an asteroid for the first time. So it'll be the first actual in-space empirical test of our ability to kinetically impact an asteroid and see what the result of that will be. There'll be lots and lots. Anyway, it'll be very useful. Let's just say that. I wanted to give credit here to Johns Hopkins Applied Physics Lab. Let me go back in the upper right-hand corner there. You may or may not know about them. JPL, the Jet Propulsion Lab, is well known. They get a lot of press. APL is almost equally important. I launched one of their small spacecraft from the adjacent launch site to the one that launched DART here at Vandenberg in 1968. So APL has been around a long time, had lots of successes like the New Horizon spacecraft, and I want to give them credit. So DART was conceived, designed, built, and will be operated by them. But in addition, many other players in the DART mission, JPL as well as NASA centers and some commercial companies, universities, technical institutes, and so on. As with most large NASA missions, there are lots of players involved, but APL is the lead. So without droning on any longer, I wanted to show you a video of what has happened and what is about to take place. And as you see here, it was Vandenberg, no longer Air Force Base, but Space Force Base. Same place, same launch site, same mission, just they changed the name now that there's a Space Force. And last November, a Falcon 9 rocket launched the DART spacecraft. So here we go. The launch took place, the upper stage was removed, the heat shield came off, and the DART spacecraft is deployed. The solar panels rolled out about 30 feet on each side of the center of the spacecraft. The all-important camera lens was opened here, the telescope camera. Here's the double asteroid coming close to Earth next week, and that will be the closest approach and the impact. And what will happen will be the deployment of a small CubeSat, which we'll talk about in a minute, which will take the images after the impact. And as we come in towards this small asteroid, the automatic camera software system on board will center on it and hopefully impact right in the middle of this small asteroid. And so here is a better look at the double asteroid. And what we have here, it looks almost like two asteroids, but that's actually a bilobe version of the small asteroid known as Dimorphos, orbiting around the largest asteroid, Didymos, which is what's known as a binary system. And we're targeting the small one with DART. The CubeSat will deploy and will follow the impact in to take images of it. The first indication of a successful result will be that the high velocity impact of a small mass will actually shorten the orbital period of this small asteroid. Excuse me, just a second. And so we are able, by a technique I'll show in a second, to calculate the orbit of the small body, Dimorphos, around the parent body, if you will, which is a very large asteroid in the center there, Didymos. And you'll see how we do that, but the key is to be able to precisely calculate the orbit beforehand, which we have done, and then shortly after the impact, watch the same orbiting small asteroid and calculate a shorter orbit indicating the velocity change, which is, of course, what we want to get with a kinetic impact. So the DART impact will actually take place at a very easy to predict time with orbital mechanics. Everything's happened right on schedule since last November. And at 7:14 next Monday evening, you'll be able to view, if you wish, the DART impact on NASA TV, and I'll give you that information in a minute. So let's look at that double asteroid target for just a second. Didymos is a very dangerous size. I talked about 1 kilometer or larger, and it's the better part of a kilometer. So if it ever happened to hit Earth, and it's a near-Earth object, but its orbit is not going to bring it near to Earth for the decades ahead as far as we can calculate, it would be a very dangerous impact. The smaller asteroid you can see there at the left, but let's kind of get an idea of the sizes here. And the Didymos at 800 meters is somewhere between the height of the World Trade Center and the largest building in the world, the Burj Khalifa, but it's much, much more massive than either of them. The orbiting small asteroid that's our target is Dimorphos, and you get an idea there for its size. Most importantly, for its mass, it's about the same size and mass as the Great Pyramid. And another way I like to look at it is if it were to hover over the Colosseum, that's about how big it is. So it's no small thing, even though I'm referring to it as a small asteroid. As I said, it's much bigger than the ones that hit Tunguska and Chelyabinsk and Arizona. As far as what we're going to hit it with, that's the DART spacecraft, much smaller, as you can see. In its largest dimension, it's only a bit longer than a bus. And most of the mass is in the center because most of the length of it is just solar panels. And so we're counting on the velocity as opposed to the mass to cause the momentum change. You may remember a little bit of science that says mass times velocity is momentum. And so we have a small mass hitting a large mass, but we have a very high velocity for that small mass. Here is the way that we've been observing the double asteroid system from Earth so far and measuring its the orbit, I should say the period, the orbital period of the small asteroid using ground-based telescopes. This is Lowell out in Arizona. A number of other ground-based telescopes here have gotten into the act and had confirmed and made very accurate measurements of the light curve of the double asteroid system, which allows us to estimate the period or calculate the period is a better way to say it. And they did it over and over again for a couple of years, you see there. And then the system went further out from Earth for these telescopes to see until just July of 2022. And since July, they have the asteroid system has come back in closer to Earth in its orbit, and it will be at its closest approach coming up in the next few weeks here. But starting in July, they could acquire it again with these telescopes and update and calculate that the period hadn't changed in those couple of years. You wouldn't expect it to, but we want to make sure to have a precise way to calculate it. So here is the technique that's used for binary systems, two-body systems, where one body orbits around another one very reliably and is in a favorable geometry, which is to say that we're looking to it in the plane of the orbit of the small body, so that as the light curve you see there on the bottom shows the sum total of the brightness when you have both bodies sharing the light. And then when the small body goes behind, you can see the small dip there. And when the small body goes in front, you can see a much larger dip. And so this happens over and over again for days and months and years and centuries and so on, and is very reliable. And so we have precise measurements of the orbit of Dimorphos about Didymos. It's about 11.9 hours. And we expect that with the collision, there will be on the order of a 1% change in the period, which is somewhere around 7 to 10 minutes or so. So those ground-based telescopes will be competing to see who can get the first precise measurement of the new period afterwards, which we should know about within the next weeks, I think. The other thing that we're looking for, in addition to the momentum change from impacting it at a high velocity, is known as beta. And simply put, beta is the result of the material that when the impact occurs, as you see in this computer model of it here, is ejected out of the crater that's created. And that ejecta, that material that's blown out in the opposite direction, adds to the change in the velocity in the same way that Newton talked about action, which is that, and reaction, which is the ejecta going out in the opposite direction. So they will help to change the momentum, change the velocity, and the modeling of it, as you can see here now, a rubble pile of very small grains to medium size to large rocks as a rubble pile, and it will dig out a crater that they estimate to be 15 feet across and 10 feet deep. And I can tell you right now that we know little enough about the actual surface crust, if there is any, for a small asteroid, or the density of the objects to have any high confidence that we can actually accurately model this. We're going to learn a lot from the first ever empirical test that will have lots of measurements taken on it. So that's the mechanism, and we're going to see what actually will happen. So here now is finally a look at the simple view of the spacecraft. And you see Draco, which is the automated telescope imager that is all important because it picks up the double asteroid system initially, and eventually, as we get close, is looking at the small asteroid and keeping it centered. On the side there, you see Lichia Cube, which I'll talk about in just a second. It's a very commonly used kind of thing called a CubeSat these days. They're very small, but very repeatable and have great functionality for simple missions. The measurements you see about a little over 6 feet in diameter and about 8 feet or so in height. We'll get a look at that in just a second, but it's not very large. You can see the mass up there. I'll translate it into the familiar pounds. Once the hydrazine thrusters that you see there in the flipped around view of the spacecraft in the middle, which are on the other side from the camera and are used to correct the course of the whole spacecraft as we center in towards the double asteroid, and eventually tweak the aiming so that we can aim for the center point of the small one. So they're very important. And on the side, you see the high gain antenna, which will send down constantly the imagery from the Draco camera. But the 1,210 pounds is what they estimate it'll be after the hydrazine from guiding the mass in takes place, will be about all that the mass is. That's about the size, or actually a little bit less than a smart car, if you want to have a feeling for what it is. Another way to look at it, to see actually what it is to look at the spacecraft all prepared with the solar panels rolled up at the side there in the lab just before it was taken to the booster to be mated to the top for launch. And you still need to kind of get some perspective. So I thought Shaquille O'Neal here could help us. And so if he stood next to it, he could place his palm on the top of it. So that's how big it is. And it's roughly 3 to 4 Shaquille O'Neals in mass. So now that you have that image of him impacting the asteroid, we'll move on to the small CubeSat that will be deployed, actually was deployed 10 days before. So what's that, 4 days ago? It is flying now near the DART spacecraft. It was designed and built by the Italian Space Agency. A CubeSat is something that's become all the rage for people that don't have the budgets that NASA do, like universities and companies that want to get their smaller spacecraft up there. They're very modular and repeatable. The smallest module is known as a U. You see that 6U. Well, a U form factor to the engineers is about the size of a Kleenex box. So you can picture 3 of these next to each other and then a row of those on top of it for 6 of them. And so a 6U, which is what the Lichia cube is about that size. And the key part of it for our mission is 2 cameras, which the Italians have cleverly named Luke and Leia. Leia being what's going to give us the highest resolution images as it flies by, and Luke will give us some multispectral information that hopefully will tell us something about the composition of the asteroid. So this is going to be very critical that this CubeSat work properly in order to give us more than just the momentum change from the period information. So let's look at that operation quickly as we finish up here. 30 days ago was the time when we were provided these slides that it was expected that that telescope imager would be able to actually find the double asteroid system. Actually, Didymos is what they're going to be able to see, the larger of the 2. And in fact, it outperformed that in that on the 27th of July, about a month before 30 days, they actually did acquire Didymos with the onboard camera. So we've been watching it now for some time. At 10 days, which as I said was 4 days ago, we started using that high gain antenna to send the imagery down all the time. So we have real-time view of what the Draco camera is seeing all the time now. And we have to get down to the last day, actually coming up next Monday, the last 4 hours, we will shift into fully automated mission operations where the combination of the SmartNav software on board and the Draco camera will guide us using those thrusters, the hydrazine thrusters, to aim at the center point of the smaller asteroid. And in the last 60 minutes, believe it or not, is going to be the time. So just after 6 p.m. next Monday night, and you can watch this on NASA TV, that's as close as we need to be before we will actually see the smaller asteroid with the Draco camera, at which point it will be a little bit visible. We're at that point 24,000 kilometers or about 15,000 miles out with an hour to go. So as you can see, it will be hitting it at 15,000 miles per hour, and that's what we're counting on to give us that momentum change. And so here is a computer simulation in the yellow box there of what will happen in the hour, final hour as we approach. And in the box there is the information that's being sent down. The blue flashing bars above it are the thrusters that are needed in this simulation to keep the dual asteroid system centered. And eventually, and I'll move forward here towards the end, we get down to where we can actually easily resolve Dimorphos, the smaller one. We're down to 3 minutes before impact, and the animation slows down for the last couple minutes here. As we come in, we don't need much more help from the thrusters to keep centered on Dimorphos, and eventually we'll be able to find the center of it. This will incidentally be the first time we've ever seen what it looks like. And we come down to the 0 point, not very exciting here in the animation, and impact it. And so that will occur, as I said, at 7:14 next Monday. You can watch it on NASA TV. If you've never watched NASA TV, some cable systems or fiber systems have this as one of the channels. I don't believe, at least the level of Verizon's Fios that I have, has NASA TV. It's very easy to find with your browser. You just put the word NASA TV into your Google browser or whatever browser, and it'll find the website for the NASA TV. And you can go there and you can watch it, starting with a live telecast from NASA at 6 p.m. Or, as I said, maybe it's on the TV channels that you get as well. And so if we could be out there watching, here's, if you will, the God's eye view of what's going to happen in those last minutes. And we come in towards the asteroid, center on it, and hopefully create a significant crater and enough ejecta to actually add some extra oomph to changing the velocity of the asteroid. So what I want you to think about, because you folks are insiders now, you know that any pictures you will see in the press releases or videos like this one, which are being distributed to a lot of people at this point, you can be sure that what you're looking at there as the Dimorphos small asteroid target is not what it is. We haven't seen it yet. It's far too small to see with ground-based or even space-based telescopes unless they're very close. We won't actually see it until Dimorphos gets up there in the last, or I should say Draco is up there looking for it in the last few hours before the impact. And so we'll be discovering together. And so you're an insider to know that what's in the press releases is not what's so. We'll see what's so when we get there. So that's it for the DART mission. And now I'll point out that DART, as many things with planetary defense, is an international activity. NASA's doing its part to impact the asteroid for the first kinetic test, but the European Space Agency also has a spacecraft. It's that block of cheese-looking thing there known as Hera, and it will be launched in about 2 years. And instead of impacting our Dimorphos asteroid, it will rendezvous with it. It will go in towards there. It will go into orbit around it. It has special instrumentation on board so that we will get much more information when it rendezvous in 2026 and do a crash scene investigation, if you will. It'll give us a much better calculation of the mass of Dimorphos, much more detail, hopefully, of the size and shape and the ejecta around the crater. Using these instruments you see at the bottom there, the LiDAR will allow us to actually look at the topography of the asteroid. So we'll understand the target that we've impacted much better. We'll get much more information about the composition of the asteroid and the ejecta. They may have a couple CubeSats on board. They aren't finished designing that part of it yet. And they may actually have one of the CubeSats land on the surface as well. So that's coming up. I wish it were sooner, but it's launching in a couple of years with more information about the kinetic impact in 2026. And I'll finish with this picture that you may recognize of the rock group Queen. There's, what's his name, Freddie Mercury in the front there. And I'm not putting this up there to show him so much as this guy. And some of you may know about that guy. He's the lead guitarist. His name's Brian May. He also is a world famous astrophysicist. And here he is today, looking like an 18th century English barrister or something. But that's what he looks like today. And I show him for the reason that he narrates for the European Space Agency a wonderful video of the Hera mission, if you want to learn more about it. I haven't had a chance to talk about that part of planetary defense, but it's an exciting upcoming mission. The other part from DART, and you can go to that webpage and listen to him and watch what Hera is going to do. I really recommend it. It's one of the better videos I've seen. As I said, he's an astrophysicist. He's well known in the NEO and asteroid community. Quite a serious scientist, as well as playing good rock guitar. So that's it. And I'm eager for any questions you may have. Thanks for letting me take so long to do this.
Okay, John, thank you very much for an outstanding presentation.
Good. Glad you liked it.
So first I'm gonna say, if any of you have a time constraint and need to leave, feel free. John will take a few questions if you want to sit around and ask him some questions. Is that okay, John?
That's great.
Okay. Any questions from you guys here? Dave?
I have one. What's the chance that this could be not solid, but liquid? Like Dimorphos or one of the others?
That the asteroid would be literally a liquid.
Yeah, or
There's no chance that it will be a liquid simply because of the cold of space. But it's a very good question in the sense that we have now learned from another asteroid that we visited, known as, what's the name of it? At any rate, there was a NASA spacecraft, OSIRIS-REx, which took a sample from another spacecraft that's almost as large as the larger of these two about 3 years ago, and the material from that is coming soon back to Earth so we can actually look at that material. My point, though, is that's a much more massive object, which we recently didn't impact, but they went down to the surface, puffed it with compressed gas, and found that they had created a much larger crater than they had predicted. And most of the reason for that was the surface material had much less cohesion than they expected, and they dug a huge crater, as it turned out, where they had expected to have only a very small hole. And so they've been very surprised. This information just came out after these slides were given to us some 4 or 5 months ago. This information came out from NASA Goddard studies only in July. So the recent information shows that an even larger asteroid has a surface, and I'll quote them, the researchers here, that has a surface that flows more like a fluid than like a crust that they had expected to hit. So it's not going to be liquid, but it's going to probably act more like a liquid than we might have expected. We're finding small asteroids don't have as much crust and cohesion, at least in the cases we've looked at, than we thought. And that will have, not to, no pun intended, it will have an impact on the actual characteristics of this impact. It may mean that there will be a lot more energy absorption by the surface of the asteroid in creating the crater, and therefore less momentum transfer. It could be that we will have less, again, the word impact, than we expect to have on the velocity. And so we're learning all the time. This is the world's first actual live asteroid deflection by kinetic impact test, and we're going to learn a lot from it. It's not a liquid asteroid, we're sure of that, but the nature of it as a solid rubble pile, we're going to be learning a lot from.
Yeah, Nancy has a question. Yeah,
Yeah, back in my middle school science teaching days, I was the beneficiary of some fabulous programs that were NASA sponsored, primarily out at Penn State, Maine. And I'm wondering if NASA is still investing in educating teachers, because that certainly was very exciting for me and all of the other teachers who were there. And that excitement gets transferred to perhaps one of the potentially most valuable target audiences when you're looking at possibly engaging and exciting 12, 13-year-olds. You know, that's our next generation of potential physicists and astro scientists and whatever. So is NASA still educating teachers as a part of their missions? My questions.
And the answer is a resounding yes. I've dealt with the government in especially the Defense Department and the intelligence community, but also NASA with leading studies for NASA through the years of my career. NASA does by far the best job of any agency of public relations, but also deeper substantive public interaction. And they have a very well directed and sponsored program to teachers. And they have regular outreaches to allow teachers to be involved. They have tutorials as well as actually physical programs where teachers are selected and get to go to NASA sites to get the up close and personal kind of briefings. They have regular briefings, literally weekly, with one or another school having their real-time interaction with the International Space Station astronauts. That happens all the time. The program I'm in, the NASA Ambassadors, is hundreds of us that all work through JPL. I think I told you before, it's one funded person on the JPL Caltech contract that runs it, and 700, 800, however many of us across the country that work for nothing. And it's because we love space, and this is actually fun, especially for those of us that are retirees. But I wanted to make the point to your question that I think probably the majority of those hundreds are teachers, okay? And so they get direct information, as I do, from the NASA scientists and engineers and university people on NASA programs that talk to us and provide us materials all the time. So it's very effective outreach to teachers, especially, I'd say.
Thank you very much.
Sure.
Dave Walter.
We've all heard about Murphy's Law and law of unintended consequences. Is there any danger that there might be some miscalculations that would actually move one of these objects towards the Earth instead of away?
It's an excellent question. I've given this talk half a dozen times now in various forums, and one smart person or another always kind of gets around to that question. The fact is, this double asteroid system, you might wonder, why was that selected? Well, it was selected for a number of reasons. And one of them is that the answer to your question is no, there's no chance. And the reason we can say that with confidence is the mass of this double asteroid system is dominated by the center. We aren't hitting the center, and we aren't doing much for the little body that's going around it. And even if we did enough to blast it to smithereens, the same mass would still be orbiting in pieces around the center, and you'd have the same mass as there is today, and we aren't hitting the one, which is Didymos, the center asteroid, and we can't hit it. And even if we did, it would have no particular impact with its mass and our small mass. So the answer is no, there's no chance of it. And that's why we chose to hit a small asteroid like Dimorphos, but not one that's orbiting by itself and might actually change its velocity going around the sun. This is only changing its velocity going around a parent, and it might change its orbital period, but it'll still be the same amount of mass in pieces, if you will, but it's not likely to do much. But there's no chance of causing any hazard from this, no.
And what keeps our satellites from hitting all of these meteors?
Hitting the near-Earth objects?
Yes.
Our satellites, which are literally a cloud, you're probably aware now, a dangerous cloud in terms of hitting one another. And our satellites include useful things like the several thousand that are actually still performing missions, to the much larger number of thousands that are dead satellites, or worse, rocket bodies that are still up there from the 60s or 70s or 80s. They're all up there, and it creates quite a traffic jam, and it's kept track of constantly by an Air Force set of ground-based telescopes. And there are regular alerts, not just to the International Space Station, but to other satellites in order to tell them to be careful and get out of the way of something if they have the capability. So it is a dangerous zone, but it exists only for pretty much the first 500 miles out from the surface of the Earth. The NEOs that we're talking about don't orbit that close. As I said, you can look at the close approaches, and some of those close approaches that you see may get within the distance to the moon. Very rarely does that happen. So that's most of the answer. Even if they came in close, space is a big place. And even with what I've referred to as a cloud, there's a whole lot of space between everything all the time. The probability of anything getting within hundreds of miles of Earth in its close approach and also hitting something is vanishingly small. That's just a matter of probabilities. Doesn't say it couldn't happen, but almost impossible to happen.
Okay, John, it's been a wonderful morning of education. And I know for one, I'm going to go check out some of those websites on your presentation. We've recorded it. We've recorded the presentation, so anybody can go back.
One more question.
Oh,
Larry, up there.
You're on mute, Larry.
Thank you.
There we go.
My question is about the recording. When will it be available? I have a couple of
Probably
grandchildren.
will be on. Lynn will probably get it uploaded by tomorrow.
Okay, thank you.
You know where they are. They're on the westminster.org website. Go down and hit the YouTube icon.
I'm sure I can find it.
Yeah, okay. So
Thank
that's,
And thank you, John.
I really appreciated it. Love to talk to you folks. Take care.
all right, thank you. That's it for the day.
Rob Soursby's get to know each other.
All right, yeah, next week we have, I'm prepared to have fun and be directed by Rob and his fun and games. Thank you.